Welcome back, and let us resume our discussion on the flip flops and the counter design using these flip flops. So, we just discussed the overall operation of a level sensitive latch, and from there how do we get an edge sensitive flip flop, positive and negative edge triggered. From there we can go ahead and try to construct our counter that we discussed in the very beginning. So, once again if I look at the counter operation, I can construct it in two fashions. One is asynchronous counter, which is called ripple counter, and second one is going to be synchronous counter. Let us see the distinction between these two. Let us first look at a ripple counter, which is an asynchronous counter, and we will see why do we call it asynchronous or a ripple counter. So, we will revert back to our truth table for the counting operation and try to implement the overall scheme, where each of these flip flop stages in a chain are implementing the division of clock frequency. So, once again if I look at the clock waveform and try to see how these flip flops are going to be employed to construct the counting operation. Suppose to begin with, all the flip flops were set to 0, that means their outputs was 0, and suppose I assume that all of them are negative edge sensitive, that means they are going to make transitions at the negative edge of the clock at these points. So, the waveform that I expect is that the first one, or the LSB, should be toggling at every negative edge of the clock. So, you have these as the negative edges of the clock, so at this is the expected behavior that I want. So, at the next negative edge of the clock, again it should go down at the next negative edge, going up and down and so on. And likewise, we have the second flip flop, that is the second LSB, that should be once again transitioning when the first LSB is making a high to low transition. So, if we look at the behavior, expected behavior of the second LSB, it should be going high over here, and then once again when the next high to low transition in the LSB is happening, it should be going down and so on, once again going up when there is a high to low transition in the first LSB, right. So, if I look at the count that is getting implemented here, if I call this you are having 0 0 after this positive edge of the clock, after first negative edge of the clock you are having 1 0, after the second negative edge of the clock you are having 1 0, and then you are having 1 1 and so on. So, if I look at the third one, for example, third one once again is expected to make transition at the negative edge of the second bit. So, if it is 0 starting from 0, it will be going high here and so on. So, after this it becomes 1 1 1 0 0 1 and so on. So, this is if you see, this is the overall counting operation that you are able to implement from 0 0 0 1 2 3 4, and likewise it will be continuing. So, this is the operation I want for my flip flops. So, this is what I want to implement using the flip flops. So, the first bit, that is the least significant bit, or the LSB, making transitions at the negative edge of the clock, starting from all 0, the first flip flop is making transitions at the negative edge, going up, again at the next positive negative edge, going down, next negative edge, going up. So, it is toggling every alternate negative edge of the clock. Just like in the truth table, we have the LSB toggling after every for every entry in the truth table, we have the LSB toggling, and the second LSB toggles when we have the LSB toggling from 1 to 0. So, again it goes to 1 1, again the LSB going from 1 to 0, again it goes to from 1 to 0. So, the second LSB toggles at the downgoing transition of the first LSB. That means, when the first LSB is going from high to low, the second LSB will be making transition. Again here we can see the first LSB going from high to low, the second LSB making transition. Likewise, the third LSB, it is going to make transition when the negative going transition of the second LSB happens. For example, if I look at the second one, whenever it is making a transition from high to low, that is means the negative going transition of the second LSB, it is going to make transition over here. So, the third LSB, it makes transition when you are having a negative going transition in the second LSB. So, each of these are toggling the state, each of these are toggling their states at the negative going transition of the previous stream. So, if I call this say Q1, Q2, Q3, so what we can observe is that Q1 is supposed to make transition at the negative, or Q1 is supposed to toggle at the negative edge of the clock. Toggle means it is just going to reverse its state irrespective of whatever data input is coming. We are not relying on any external data, it is just supposed to reverse the state from 0 to 1, 1 to 0, 0 to 1, 1 to 0 whenever the negative edge of the clock is coming. Likewise, Q2 is going to reverse its state or toggle whenever the negative going transition in Q1 is happening. So, if you look at the negative edge of the Q1, the Q2 goes from 0 to 1. Likewise, the second negative edge of Q1, Q2 goes from 1 to 0. Third negative edge of Q1, Q2 goes from 0 to 1. So, whenever a negative going edge in Q1 is appearing, Q2 is making a transition or it is toggling from its previous state. It is changing its state from 0 to 1, 1 to 0 and so on. Likewise, same thing for Q3. Q3 is going to toggle or change its state when the negative going edge of Q2 is appearing. So, here Q2 is going from 1 to 0, as a result Q3 is going to make a transition from 0 to 1, it is toggling. So, this is the overall toggling operation that we have to implement using each of these flip flops and make sure that they toggle at the previous or the negative going transition of the previous output. So, at this level, of course, I can estimate or I can guess that yes, the Q1 can act like the clock for Q2. So, I can use Q1 as a clock and implement Q2 using a negative edge sensitive flip flop. So, that whenever there is a negative going edge or negative transition in Q1, that acts like a clock for Q2 and therefore, Q2 is going to make a transition. At that transition is just reverse. So, if it was 0 before, it should go to 1, if it was 1 before, it should go to 0, that is what I expect. Likewise, for Q3, Q2 can be used as a clock. If I use if I use a negative edge triggered flip flop to implement Q3, I can try to use Q2 as the clock for Q3. Now, Q3 being a negative edge sensitive flip flop, whenever there is a negative transition in the clock of Q3, if you are using Q2 as the clock of Q3 and there is a negative edge in the Q2, then the Q3 should be making a transition, and that transition should be just reversing the state of Q3. So, Q3 should be toggling from 0 to 1, that is what we want. So, this is clear that definitely we can use Q1 as a clock for Q2, Q2 as a clock for Q3, and make sure that Q1, Q2, Q3 are all negative edge sensitive. And the other requirement is that at the negative edge of the clocks, these flip flops should be flipping their state. If the state was 1, it should be going to 0. If the state was 0, it should be going to 1. So, we do not need a data, external data to implement that. What we need is the information about the previous state of the flip flop itself. If we know that state, we just need to make sure that the flip flop is acquiring reverse of that state. So, if the Q3 output was available to me and it was 0, I want to make sure that the next time at the negative edge of the Q2, Q3 is transitioning to 1. So, how can I implement that? One logical way will be to put the D of Q3 equal to the naught of Q3 is the previous state, right. So, if I have the latch available where you have the D and Q and you have the negative edge sensitive clock. So, for negative edge sensitive clock we will put this triangle to denote that it is edge sensitive and another bubble to show that it is negative edge sensitive, and I have the Q over here, and if I want to make sure that it toggles the state. So, I would like to I can simply put a, if I have say an inverter and if I put the Q over here. So, that would make sure that when the Q was say 1, here you had a 0 available before the negative edge of the clock. So, if it is a clock and you are looking at the any of the negative edge of the clock, if Q was 1 before the negative edge of the clock, we know that the Q bar over here, bar means the inversion of Q, logical inversion of Q. So, if this was 1, Q bar was low. As a result, at the next positive edge of the clock, if the Q was high, the Q will be making a transition from high to low. Likewise, at the next negative edge of the clock, the Q1 or the Q bar will be high because Q is low. So, at the next negative edge of the clock, since the D input was high, because it being Q bar, it will once again make a transition from low to high. So, this is all I need to do to make sure that this flip flop toggles its state after every negative edge. This is clear, and in general I do not need this inverter explicitly. The flip flops do have the complementary outputs coming in. So, in most circuit implementation of the flip flop, you will have the Q and Q bar, the logical inversion of Q bar also available from the flip flop circuit. So, I can use the Q bar to implement the toggling operation. I can simply connect the Q bar to the D input, and this is going to make sure that at every negative edge of the clock, the flip flop output Q is going to flip its state from 0 to 1, 1 to 0 and so on. So, this can be called as a toggle flip flop, because at every negative edge of the clock it is going to toggle its state from 1 to 0, 0 to 1 and so on. Likewise, you can have positive edge sensitive toggle flip flop also. So, here you are using the D flip flop to construct a toggle flip flop, which is going to be useful in implementing our counter. So, we have the basic unit for implementing our counter available over here, and all we need to do in order to implement this functionality is to cascade such blocks. How do we cascade? The first flip flop in the chain should be receiving the main clock, the input clock, and as we said, the output of the first clock should be acting like the output of the first flip flop should be acting like the clock to the next flip flop. So, that at the negative edge of the transition of the first flip flop, the second flip flop is getting triggered. So, I have these the first one is going to receive the main clock, which is going to make this one toggle at every negative edge, and then I would like to put the Q of the previous flip flop as the clock of the next flip flop. So, that whenever the, if I call this say Q1 D1, whenever Q1 is making a negative transition, the Q2 toggles its state. So, all I need to do is Q2 and Q2 bar, and this is your D2, and once again and we go on repeating this structure. And so on, sorry, and so on. So, this is what we need to do. We need to cascade this structure to obtain an n bit counter, and now we need to answer the question, why do we call it a ripple counter. So, if you look at the first flip flop, that is receiving the main clock from the system, and at the transition of the first flip flop, at the negative transition of the first flip flop, the D2 is changing its state. Then at the transition of the second flip flop, the D3 is changing its state, and so on. In actual circuits that we are going to see for implementing these flip flops, there is going to be a delay between the negative transition of the clock and the transition of Q1. So, we know that digital circuitry, whenever we are talking about CMOS digital circuitry, inverters or any digital logic block, they have their own inherent delays, and therefore, if I look at the waveforms corresponding to this arrangement, we have the original clock coming over here, the Q1 is going to have a delay with respect to the negative edge of the clock. So, it is going to make transition only after a certain finite amount of delay after the negative edge. So, it is going to toggle after a certain delay. We can call this delay at T clock to Q, C to Q. So, is with respect to the downgoing edge of the clock, what is the time taken by the flip flop to change its state. So, ideally, of course, in our simulation waveform, it should change instantaneously whenever the clock is going low. Ideal flip flop should transition immediately at the negative edge as per our definition, but because of the inherent delays in the circuitry implementing these flip flop, there will be a finite C to Q delay, and as a result, it will be transitioning only after a finite delay. Likewise, after every edge, there will be this finite delay in the transition, from high to low transition as well as low to high transition, there will be a finite delay. Likewise, if I look at the behavior of Q3, so this is your Q1, this is your main clock, and then you have the Q2. So, Q2, how is it going to behave? So, here, since it is once again negative level sensitive, so it is supposed to make transition immediately when the Q1 goes low, but once again, rather than going down exactly at this instance, it will have some finite delay. If I assume the same delay, then again it is going to transition after T C Q. Likewise, at this point, once again it is going to transition after a delay T C Q. So, with respect to this, another T C Q. So, if I look at the delay of the transition of Q2 with respect to the original negative edge of the clock, we can see there is going to be a 2 T C Q delay. So, with respect to the negative edge of the clock, you have 2 T C Q delay for Q2. Likewise, if I look for Q3's waveform, it is supposed to make transition at the negative going edge of Q2. So, once again we will start from here and stretch all the way, and it is going to make transition at the negative edge of the the Q2, but after another T C Q delay. and therefore, what is the overall delay that Q3 is having, the transition of Q3 is having with the original negative edge of the clock, we are having 3 CQ delay. So, you have an overall 3 TCQ delay. Likewise, if you go on further and deeper into the chain, you will have n TCQ delay for the n stages of the counter, and therefore, what we can say is with respect to the negative transition of the main clock, the outputs are transitioning or rippling from the first output going to the second, third, fourth, and so on. So, there is a ripple going on, just like you drop a stone in a pond, where still water, and you drop a stone, and then you have ripples going on step by step. The same thing, you are having a negative transition over here, and then gradually step by step all are transitioning at the subsequent negative edges after certain delays. So, there is a delay when you put a stone over here and the ripple generates, it is taking some time, finally step by step, and it is finally reaching the shore. So, likewise here after the negative transition of the main clock, step by step you are having these transitions after each TCQ delay, finally after n TCQ delay you are having the final output transitioning. So, this is the concept of ripple counter. All the flip flops are not changing simultaneously at the negative edge of the clock, just like we draw here ideally. In the ideal waveform, this is the picture, and we expect that at the negative edge of the clock all the transitions are happening, but in the actual circuitry, because of the delay of the implementing circuitry, we will have a rippling effect. So, this is called the ripple counter or asynchronous counter. The other flip flops, apart from the first flip flop, the other flip flops are not strictly edge triggered by the main clock, they are triggered by the previous clock. So, a synchronous circuit is one in which a single clock governs the transition for all flip flops. So, here the main clock is governing the transition of only first flip flop, the other flip flops are not strictly changing their state exactly at the negative transition of the main clock, they are changing their state at the transition of the respective inputs. So, with respect to the main clock, they are asynchronous, they are changing asynchronously. So, this is asynchronous counter or a ripple counter. We can have a synchronous counter as well, where we have all the flip flops changing their state simultaneously. We will briefly discuss that, and that can be useful when your clock frequency required is high and your data rate is high, then we may need to go for a synchronous counter. Before we discuss briefly the synchronous counter, which we are not going to use in our design, but just to distinguish it from the synchronous counter, we can have a very brief discussion. Here, how does these delay relate to our original design specification, and what should be the limitation on the TCQ for our particular application. So, if you remember, the main clock that is coming in our design, we have decided a certain clock frequency for the main clock. If you remember, it was around, I think, 250 kilohertz, considering the data rate, considering the sampling frequency and the resolution of the bit that we had. The main we are having around 2 kilohertz sampling rate, and therefore, within 0.5 millisecond we want around 127 pulses of the clock, so that we can count 127 levels, and therefore, we arrive at this 250 kilohertz requirement for the clock, and we would therefore like that the ripple should be through within one clock period. So, if it is negative edge sensitive and the data transition start or the counter starts transitioning from here, before the next negative edge of the clock, the counter output should be available, or in other words, n times TCQ should be less than the period of the clock that we are looking at, TCLK in this case. So, n is the number of bits. If you are having 7 bit in the counter, you are having 7 such flip flops, and the output will be coming after n TCQ delay, and that should be lower than the clock period that we are having. Now, here if we look at the numbers that we can get from 180 nanometer CMOS technology, which you are using in your simulations, we will see that the TCQ at the transistor level circuitry it can be comfortably within 100 picosecond, a few tenths of picosecond to 100 picosecond. If you design it aggressively, it can be brought down to 10 picosecond around. For 180 nanometer, 100 picosecond can be a safe limit, and therefore, for 7 stages you just have around this number is around 700 picosecond, less than nanosecond. So, just 0.1 less than 0.1 nanosecond, sorry, less than 1 nanosecond. And as a result, if I look at the clock period that we have, it is 250 kilohertz, not even 1 megahertz. As a result, this 1 nanosecond delay is going to be comfortable enough for our application. But once again, as we target higher number of bits, there of course, the clock period will go on halving every bit, every single bit increase, and then the delay of the flip flops can become critical component in the design. As of now, in our application, we will see that this delay is not going to be critical, but we should just be aware that if you are trying to extend this concept to different design spec, having higher number of resolution, where the required clock frequency is increasing, there of course, at finally when you go on adding from 7 to 8, 8 to 9, 10, 11 and so many bits, each addition of bit doubles the clock frequency, and as a result you may for higher number of bits you may approach close to the delay of the flip flop, and in those cases the ripple flip flop or the ripple counter may not be a good option. If you are going for higher number of bits, we may like to go for synchronous counter, where we can ensure that all the flip flops are making transition at the same point. They are synchronous with the clock. Whenever the clock is having a transition from high to low, all the flip flops are changing exactly at the same time. So, that is the concept of synchronous counter. We are not going to use in this design, but you should just be aware of that concept. So, very briefly we can just discuss what is the way in which the synchronous counter is implemented. So, that leads to the concept of state machine that you might have encountered in digital electronics. So, the state machine basically stores the states of the flip flop, stores the states of the logic in the flip flop. So, suppose you have 4-bit counter and you have the outputs Q1, Q2, Q3, Q4 coming in. So, at a particular clock, they are all driven by the same clock. So, suppose they are all negative edge triggered, all driven by the same clock. So, the clock is going to all of them, and there are the toggle flip flop. So, every clock edge they can change their state, or I can use the D flip flop. I can just have the D flip flop. So, by definition, whatever is the D input available over here, I can the D1, D2, D3 and D4. So, whatever is the D1, D2, D3, D4 inputs available, according to that at the negative going edge, the Q1, Q2, Q3, Q4 will be changing the state. Here I have to make sure that this Q1, Q2, Q3, Q4 they follow the truth table that I want. So, just like the truth table that we discussed, the transition in Q1, Q2, Q3, Q4 should follow this truth table, and for that I need to figure out that if the present state of Q1, Q2, Q3, Q4 is a certain number, a certain bit configuration, what is going to be the next state. So, for that I need to construct a output state for given truth table. So, avoiding the repetition, I am just using this truth table already drawn. So, if I look at the first, second, third, fourth, fifth and subsequent cycles, at the first cycle the output of C1, C2, C3, C4 were all 0. So, what do I expect should be the state for C1, C2, C3, C4 at the next cycle should be 0, 0, 0, 1. Likewise, at the second cycle the output of the flip flop is 0, 0, 0, 1. I expect that the outputs of the flip flop in the next cycle should become 0, 0, 1, 0. Likewise, if the output of the flip flops in the second cycle was 0, 0, 1, 0, I would like that in the third cycle it should become so on. Now, how do I make sure that if the output in the previous state or the flip flop output in the previous state was this. How do I make sure that in the next state the output becomes this? I just need to make sure that the D inputs are these, right. So, if I have D1, D2, D3 and D4, I would like to make sure that these D inputs D1, D2, D3, D4 are these particular values. So, that when the next positive edge comes, previous state of the flip flop, previous values of the flip flop output Q1, Q2, Q3, Q4 were these. If I make the D input such that numbering is just opposite. So, I should just follow that convention D2 and D1. So, C1, C2, C3, C4, D1, D2, D3, D4. So, if I make sure that the D input for the next cycle is 1 0 0 0, then of course, at the next negative edge of the clock, the flip flop will be changing state, the C1 will be going from 0 to 1, others will be remaining 0. Likewise, at the second stage, if I make sure that the D inputs are like this 0 0 1 0, previous state of the flip flop or output of the flip flop was 0 0 0 1, next negative edge of the clock comes, and therefore, the D inputs that were available to all these flip flop will be copied to the output state, and as a result the flip flop will be turning to 0 0 1 0. So, basically I have to make sure that these are the D inputs, this is the way D inputs are going to change as per the previous values of C. So, basically how do I implement this? I can implement the truth table of each of these D's, D1, D2, D3, D4 as a function of the C1, C2, C3, C4. That means, the previous state, depending upon the previous state, whatever was the value of C1, C2, C3, C4, for that I have a dependency of this D4. So, D4 is going to have a truth table with respect to the previous state of C1, C2, C3, C4. Likewise, D3 is going to have a truth table, and each of these can be implemented using a K map. You can reduce it, 4 inputs, you can conveniently reduce it and try to arrive at the logic which is going to give me the D, the value of D4 or a logic function for D4 as a function of the previous outputs. So, if I have the previous outputs, I can call it Q n minus 1, means previous step output Q n minus 1, 1, 2, 3, 4 available in the previous state. I will have a logic function f which is going to give me the individual, if I call this f1, this is supposed to give me the logic state d1. So, that d1 as a function of previous q states Q1, Q2, Q3, Q4 is available. So, that I can apply it to the first flip flop input, and in the next state according to this d1 the Q1 makes a transition. Likewise, I will have the logic functions implemented using logic gates for each of these. So, you have the previous state Q1, Q2, Q3, Q4, this will be implementing D2. So, this is just logic function, and then output of these logic functions will be connected to the D1, D2, D3 input over here. So, basically I have a logic function which is taking these inputs Q1, Q2, Q3, Q4 and implementing the F1, F2, F3, F4 truth tables corresponding to logic gate, that is like we discussed, and then connecting it back to the D2, D1, D2, D3, D4 and so on. So, this is going to be our synchronous counter. So, only at the negative edge of the clock all the flip flops are changing together, and how are they changing? The next state of the flip flop is determined by this D1, D2, D3 input that is available at the negative edge, and how is this determined? That is determined by the logic function that you have generated using that truth table that we just discussed. So, this is the combinational logic which is implementing the functions F1, F2, F3, F4, generating the D inputs for the flip flops, and this is a sequential element which is latching that D input and generating the next state. So, this is the sequential element which stores the state or latches the state and gives the input to the logic block. The logic block once again produces the F1, F2, F3, F4, the next state D inputs which should be going to the flip flop, and again at the next negative edge of the clock these D inputs will be latched by the flip flop to generate the Q1, Q2, Q3, Q4 outputs. So, this is an example of a state machine where you have a combinational logic implementing functions on the flip flop outputs. So, whatever the flip flop output available at the negative edge of the clock, the logic function will take those inputs, implement certain functions, and those functions will be fed to, or it will be fed to the inputs of the flip flop, so that they change state accordingly and you realize a state machine. So, so that you have a desired sequence of state in this flip flop. So, these are states of the flip flop, right. How are we implementing this? These are states of the flip flop. So, starting from 0 0 0 0 0 1 1 0 1 1, these are the 4 flip flops which are implementing the states. How many states? In this case, if you have 4 bits, you have 16 states getting implemented. Once you have 0 0 0 0, what happens? Again, once you have all 1 1 1, what happens? It will be again returning to 0 0 0 0. So, it is kind of implementing those 16 states with the help of these flip flops and the logic function. So, this is a way we can look into synchronous flip flop, implement a fully synchronous flip flop. It can be suitable for high speed application. Here the delay of course is going to be constrained by this logic. So, logic also has its delay, and you must make sure that of course, if you are going on increasing the number of flip flops, the logic is also going to become more complicated, and there we have to make sure that the logic delay is also within limit, and making sure that it is able to compute this f1, f2, f3, f4 before the next edge of the flip flop. But that can be implemented in ways where it goes relatively at a lesser rate as compared to the C2 Q delay. C2 Q delay, we say that it is going to increase linearly as you go on increasing the number of counters, number of bits in the counters. The CQQ delay goes on adding linearly. Here it is not necessary, we can make sure that the logic is faster using some special scheme. So, these are the two schemes. We are having fully synchronous counter, and then we have the ripple counter. In our design, we are going to use the ripple counter. So, let us take a small break and continue our discussion with the counter and overall control scheme that we are going to generate with the help of this counter.